I will be picking up where Chris left off. So he told you quite a bit about the basics of conformal field theory. So by now you're all experts, and we can move on to more exciting things, though we still have a bit of ground to cover. So by now you should know what the CFT is. Right? So it's a special kind of quantum field theory which has extra space-time symmetries. It's a theory that cares about angles, but not scales in some sense. And it turns out that just with this little difference, you can go very far in determining the structure of the theory, as he explained. And so one of the key points that you should have got from his lectures is that in conformal field theories have a state operator correspondence, because you can map the plane to the cylinder via conformal map. And one of the implications of this is that CFTs have an OPE, which is convergent with a finite radius of convergence. Okay? This is really the key point that allows you to make a lot of statements in CFTs that you cannot in ordinary quantum field theories. So, for instance, one of the things that he must have showed you is that in a CFT, two-point functions, they are diagonal and they are uniquely fixed by conformal symmetry. By the way, if at any point you have questions or you disagree or you actually did not learn this, just ask me. So two-point functions are fixed by conformal invariants up to a number, but this number can be removed by rescaling operators. And three-point functions, more remarkably, are also completely fixed by conformal symmetry up to a number or a discrete set of numbers, which are called OPE coefficients. Okay? So you know the two-point functions, you know the three-point functions, but this means that thanks to the OPE, you can compute any correlation function that you want, right? Because if you have some big correlator with some large string of operators, so maybe I should add a few more here. Then what you could do is, well, you know, if you know the OPE, then you know that O1, O2 can be written as a sum of some other operators, okay, with some coefficients, right? And so you can just plug this into this correlator, right, to systematically reduce the number of insertions, right? So you start with n, you end up with n minus 1, but there's an infinite sum. Then you do it again, you have a double sum, but now there's n minus 2. And you keep doing this, and at some point you'll reach just some gigantic sum of three-point functions. But the three-point functions, you know. Okay? You know that they are fixed by conformal invariants, right? So the only unknowns in this gigantic sum are the spectrum of operators, okay, which operators appear in the OPE, and the OPE coefficients. Okay? So this is usually called the CFT data. So it's a set of the quantum numbers of operators. So one of them is always going to be the conformal dimension, which I call delta. Then the spin quantum numbers. So for instance, if it's a traceless symmetric representation, then it's just a number, L. But in general, you have some Young tableau. So some representation of SOD. And then there could be other quantum numbers like electric charge or whatever, charges under some global symmetries. So you need to know all these quantum numbers. You need to know the spectrum of operators in your theory. And then you need to know how they couple. Okay? So given three operators, you need to know these lambda O1, O2, O3, and in general there could be multiple OBE coefficients, because the three-point function could have several independent conformally invariant structures. So if it's scalars, there's just one number. But if these operators have spins and that there could be several OP coefficients. But okay, this is not too important. The important is that, okay, you need to know the spectrum, you need to know these lambdas, and if you know the CFT data, then using the OPE, you can compute any correlator that you want, and this is not a formal thing, okay, because since the OPE converges, you know, this is actually a bona fide expression for the correlator, which you can just put on the computer and sum a few terms and get an accurate representation. Okay? So this is all well and good, but you already see that there seems to be an ambiguity here. Because when you start doing this reduction, you need to make a choice for which pairs of operators you are going to multiply. Okay? So if you have operators A, B, C, then you could take the OPE AB and then BC. But you could also do A, BC, right? So you can do it in many ways. So one important requirement is that it should not matter in which way you do this. In other words, the OPE should be associative. And this is essentially a consequence of Bose or Fermi symmetry, right? So you can swap the operators and nothing should happen. So yes, so one way of thinking about this then is that this property, associativity of the OPE, places very strong constraints on the CFT data, okay? So if you just give me a random set of operators and couplings, this will not be true, okay? You will not get the same result if you use the OPE one way or another, okay? So what's going to be my goal in the next 3 lectures that I will give is to show you how this constraint of associativity of the OPE together, usually we'll ask this as well, with unitarity, okay? So unitarity places certain reality conditions on these OPE coefficients. So if you put those two things together, then actually this can tell you a lot, both about specific CFTs as well as the general space of theories. Okay? Again, because these are completely general constraints which are non-perturbative in nature, which apply to any theory. Okay, so questions about this? It's kind of broad, so it's hard to ask good questions. But, so let me just show you something concrete, because this is a bit too abstract right now. So for instance, let's consider the 4-point function of 4 identical scalars. Okay? So 5x1 okay? So as you learned in Chris's lectures, you can write this in terms of some unknown function, right? So there's some prefactor, which in this case we can choose to be this. I mean, nothing forces you to do it this way, but this is one choice you can do. And then there's a function of 2 independent conformal cross ratios, which are quantities which are invariant under conformal transformations. So this U and V, you know what they are? Yes? Okay. Okay. So Chris should also have told you that. So these are just the constraints from conformal invariance. But then if you use the OPE, then you can say more. You can say that this function is actually equal to 1 plus a sum Okay? So doing DOP, so fusing these two operators and these two, you get the representation for the 4-point function in terms of these functions, which were called conformal blocks, right? These are things which are kinematical in nature. They are the same, yes, so they are kinematical in nature, so they are the same for any CFT. So you can just compute them once and for all. And this is the expression that is appropriate for the decomposition when you do DOP 1, 2, 3, 4. Okay? So you multiply operators 1, 2 and operators 3, 4. So this is a representation of the 4-point function. And we'll see shortly that it's a very nice representation. It converges quite fast. Again, this is not a formal expression. And so in this case, the quantum numbers of the operators are just the conformal dimension. And the spin quantum number, there's only one number because this is a traceless symmetric representation, which are the representations that can appear when you multiply two scalars. Okay? Good. But of course, I mean, nothing forces me to use this decomposition. So now let's do 1, 4, 2, 3. Okay, so we'll swap 2 with 4. So if you swap 2 with 4, then you can say that the correlator will be the same. So we'll just write that as 1 over x14 2 delta phi, x23 2 delta phi. And now you can do the same. So now you can write it as 1 plus the same OP coefficients, because it's the same two scalars, right? And now the conformal blocks corresponding to this decomposition. And since you've swapped 2 with 4, then you can just check that when you do this, U gets exchanged with V. Okay? So you just get G delta L V U. Okay? So these expressions are very different, right? The blocks, they are not symmetric functions of their arguments. Nevertheless, these expressions have to match. So you can write this as, so if you multiply everything by, say, this factor, then you're going to get this on one side, and on the other side you're going to get this divided by this, right? But that's the same as U over V. So you get 1 plus sum G UV must equal U over V to the delta phi, 1 plus sum okay. Or if you want, we can rearrange things slightly such that okay. So I've just rearranged this equation. And this should be 0. So out of this sum, there's a special operator, which is the operator with del equals 0 and del equals 0, which corresponds to this 1, which is the contribution of the identity operator, which always appears with coefficient 1. So it's convenient to put it to one side. Okay? So this is the crossing sum rule, okay, which has to hold for the correlation function of 4 identical scalars in any CFT. Okay? Any correlator that you compute in a CFT, if you can check that this equation has to hold. And again, it's not a formal equation, it's something that converges, and you can just check that it's actually true. Okay? So one way of thinking about this equation is that it provides a continuously infinite set of constraints on the CFT data. Okay? So it's continuously infinite because it has to be true for all u and v where this sum converges. Okay? It's a continuously infinite set of constraints on the discrete set of CFT data. And so what we'll be using in our lectures is to try to extract information from this equation. Okay? So it's believed that if you, this is one particular crossing equation, but you could play this same game for any 4-point function that you want in the theory, and it's believed that if you can solve the constraints for all sets of 4-point functions, then the solution space of these constraints is the same as the space of consistent CFTs, at least on the plane. Okay? Now you may wonder, well, what about 5-point functions, 6-point functions? Don't I need to check that those are true as well? You don't. So for the 4-point function, basically this consistency requirement can be written diagrammatically like this. So doing the OPE in this way, 1, 2, 3, 4, it's the same as doing the OPE in 1, 4, 2, 3. So this is the origin of the little drawing in the cover, in the poster of the school, right? So let's assume that this is true for any operators that exist in the theory. Then crossing symmetry will also hold for any correlator. And you can just do this diagrammatically. So for instance, imagine that you had some 5-point function, and you had done the OP in this way. Okay? 1, 2, 3, 4, 5. Okay, so these should all be double bars. Then you can use this relation, right? Here, for instance, here, on this piece of the diagram, to obtain 1, 2, 5, 3, 4. Okay? So you've used the OP such that now it's 3 and 4 which are together. Okay? So by using this, you learn this. So you've gone from one OP decomposition to the other one, and it's easy to check that you can generate all possible OP decompositions in this way, and it works not just for the 5-point function, but any n-point function. So if you've established that crossing symmetry is true for all possible 4-point functions in the theory, then basically you're done. Okay? The OP is associative. Okay, questions about this? So our approach now will be, as I said, we will investigate this equation to try to extract information. And the approach that I will describe is almost completely numerical in nature. So there are results on the analysis of this equation by analytic means. But I would say, so far, the most striking results have been obtained numerically. And this is what I will describe in these lectures. And so you see that before we start, we need to have very good control of the ingredients of that equation, numerically, which are essentially the blocks, the conformal blocks. We need to be able to compute them very efficiently. Okay? In general, these are complicated functions. So this is one thing that we'll do. The other thing I'd like to tell you is that if such a procedure has any hope of succeeding, then we would want this equation to be approximately true with not too many terms in this sum, right? Because numerically, we'll always only have a finite number of terms. We cannot have infinite. So if we need to include a lot, then probably the numerics will be hopeless. So, I mean, of course, you could just try it. You can just try to do it and see if it works, and this is how it was done historically. But it's nice to have some understanding of why this is true. Okay? So we'll also study the rate of convergence of the OP. So Chris told you that the OP converges, but it did not tell you, he did not tell you how fast it converges. So we'll also look into that. So the rough outline of what's going to follow is that we're going to discuss OP convergence first. Then everything you ever wanted to know about conformal blocks but were too afraid to ask. Then we'll actually analyze that crossing equation. What's the geometry associated with that equation, and how can we exploit that to derive constraints? Then the numerical methods which are used to actually get those constraints, and hopefully give you a sample of the kinds of results that you can get with these methods. So show you some nice plots. Okay, so questions about this? This is kind of like the general motivation. Now we're going to get down to the nitty-gritty of it. No? Okay, good. So again, interrupt me if there's something that you don't understand, if I'm going too fast. Okay, so let's consider the 4-point function in the following configuration. So the same 4-point function that I wrote down before. And I'm going to multiply this by x2 to the delta phi. X3 to the delta phi. Okay? So do you know what this means? These bras and these cats? So this is the same as having phi inserted at the origin, right? So in radial quantization, this gives you an eigenstate. And this is phi inserted at infinity. So this is the out state in radial quantization. Okay? And then I'm going to multiply by these factors just to simplify things. Okay. So Now we're going to use the OPE in this channel, where you fuse this guy with this guy, and this guy with this guy. And so what this is going to give you is the following. Some O. Okay, so this is the same as the conformal block decomposition, or rather, you can expand the conformal block also in a power series. So there are two sums here. This is the conformal block sum, so the sum over conformal primaries. So I've rewritten things here a bit. So there I was saying lambda square of delta NL, which are the quantum numbers of the intermediate operator. And here I'm just saying it's the OPE coefficient between phi, and the operator O, which is labeled by delta NL. Okay? So bear with me. And so this is the sum over descendants. Okay, so the conformal block captures the contribution of a primary state and then all the descendants. And so this sum here is over the descendants. And now these tau and these angles, so this is writing x2 is equal to e to the minus beta tau 2 and x3 n2. Yeah, I think this is correct. Maybe it's plus. No, I think this is minus. Yes.
So if you label your descendants just with K, how do you know how the degree is contracted?
So K labels the level of the descendants. Yeah. Okay? Then information about angular dependence is all put into this element. Okay?
And you can have different descendants with different contractions, so you can have like
yes.
expanded operators.
Yes. Yes, that's right. Yes. So here I'm only looking at the sum over the level of the descendants. Okay? So maybe this is this. Right. Okay. Again, these are just some matrix elements, as I said, that arise from contractions of terms on the same level. Now, notice that, so let's call this function e to the delta phi tau 3 minus tau 2. Oh, maybe I got this wrong. I think it's probably this. Tau 3 minus tau 2 times, I'm going to call it L of beta n3 dot n2. Okay? So clearly we have right? So if these points, they have different angles, so this is something which has to be rotation invariant, so it will involve some polynomials in n3, n2, which is like a cosine. And so, in general, the cosines will be smaller than 1. But if you line them up, that's the maximum size of the function that you can get. So, therefore, we can write okay. So here you had some discrete sum, and you can think of this f as some sum of delta functions, okay, with positive residues. Okay, so it's just some density which has some positivity properties.
This beta is different from the beta x.
Yes, sorry, this is wrong. There's no beta here. So this is beta. Okay, so now what can we say about this density? Well, let's use crossing symmetry. We know that when tau 3 goes to tau 2, this is the same thing as x3 approaching x2. So we can use DOP in that channel. Yes. Sorry, could you repeat that?
The inner product between M1, M2, and M3 is basically inner product between x2 and x3, right? The coordinate.
Yes. So as tau 3 approaches tau 2, you can look at the OP in this channel, and the leading contribution is that of the identity. Okay, it's the first operator appearing in the OP. So this is modules x3, phi. Okay. So as beta goes to 0, you are receiving contributions from more and more states in this sum. And the contributions, they have to add up in such a way that you get a power law divergence in beta. Okay? So. Now there's a theorem called the Hardy-Littlewood-Tauberian theorem that tells you that if you define the following function, can people see this here? Okay. For sufficiently large E star. Okay. So what's the rough idea? What you would want to say is something like, well, when beta goes to 0, this gives me a power law, right? So if little f of E would behave like e to a power, then this integral would just look like the gamma function integral. right? And it would give you the correct power in beta, okay? But since f is in general some density, the most that you can say is actually this.
Sorry. The statement of the theorem, for what L of E or L of epsilon?
Sorry, for which?
What function of epsilon is this true?
Epsilon of E.
Or E?
So this has to be positive, okay? Or a density with positive residues.
And nothing else is required and it always goes like to something. Okay.
Yes, I mean, there must be some more detailed mathematical requirements on F that as physicists we probably don't care about, but that's the rough idea.
To believe that any function of E would always integrate to
This is asymptotically. It's not any function of E, because when beta goes to 0, this has to give you a power law, right?
Oh, I see. So requiring that.
Yes, of course, yeah. So if this is true, then this has to be true, okay? Yeah, sorry if that wasn't clear. So now we can use this property to place a bound on the tail of that function L beta. Okay, so let's define L beta E star as the contribution from states with large energies above some E star. So if you're getting a bit lost with all these definitions, so this is the contribution from, say, conformal blocks with very large delta, okay, to the sum rule. This is what this means. Here, instead of using the blocks, we are actually using the descendants more generally, but in the end, we'll get a bound on the conformal blocks. So this is the picture you should have in your mind.
Would that be an exponential function in the theorem?
Sorry, here?
What happens with the exponential function?
It'll come later. Skipping ahead. This is, look, there's just f of e here. The exponential is not there. But indeed, so what you expect is that the convergence will be exponentially fast, right? Because this f is roughly going like a power law. So it's going to get killed by the exponential at some point for sufficiently large e. So once you cross the saddle, things will go exponentially fast to 0. Okay, so this you expect that it will converge exponentially fast. So this is what I'm going to show now. So we use a trick. You write that fx is dx of fx minus f of x naught. Okay, write it like this, and then you can do integral from e star plus infinity to e So there's your exponential. Okay, so we use this trick. Now there's something that we're subtracting off here, so this is smaller than this. Now we use the hardy little with asymptotics. That this function will have to become this. And then this is just an approximation of this integral. Okay?
Did you integrate by parts?
What's this?
No, to get after a substitute, for example, x with x over.
Yeah. Yeah, that's where you get this beta. You integrate by parts, you get a derivative acting on that. That gives you the beta. So okay, so we have this result. It tells you that the 4-point function, as you're doing the sum, converges exponentially fast as you include more and more states. Okay. Of course, the caveat is that there's a beta here, right? And beta is controlling the separation between x3 and x2. Okay? So this just means that if you're close to the OPE decomposition in the other channel, in the cross channel, then this estimate is very poor, right? Because to recover states in the cross channel, you need to sum basically the whole tower of states in the other channel. Okay? So in that limit, it's better to use the OP in the other channel, and you just get the identity plus low-lying operators. Okay? But for reasonable beta, the convergence is exponentially fast. Okay? Now, of course, so this is a bound on the contribution of states with delta above E star. But what we want is a bound on the blocks, right? But it's easy to see that the tail, when you include, in terms of descendants, it's always larger than the tail when you include the blocks, because with the blocks, you are subtracting the low energy blocks, but low energy blocks include an infinite set of states with levels, with energies arbitrarily high, okay? So the tail in that sum is always bounded by this one. Is that clear? So when you subtract the low energy blocks, you're also subtracting many of the states that are contributing here. So you get something smaller. Okay? So I encourage you to say, take free theory, okay? Work out the conformal block decomposition, the first few terms. You can just do it in mathematics, you just subtract the first few terms to get the OPE coefficients, or compute them by hand, you can also do that. And then check how fast this converges. So add up a few blocks and see how closely it approximates the 4-point function. And you'll find that it converges extremely fast. Okay? So this is this is not the best possible estimate. There are better estimates. But I just wanted to get the exponential fall off. Okay? Okay, questions about this? Okay. Okay, so now conformal blocks. Yes.
This is an asymptotic relation of E goes to infinity, yeah?
Yes.
So this doesn't mean that for any finite E, my sum is going to actually be
Yeah.
less than this, correct?
That's right.
So what is the statement then, rigorously? What do you say?
This is the rigorous statement.
So then we're not saying that the tail of my conformal block sum is bounded by
It falls off exponentially. So what you're wanting to ask is, when do the Hardy-Littlewood asymptotics kick in?
basically. Yeah.
Yes. So I don't think this has been shown anywhere, but you could estimate that by, if you know what's the next term in the OPE, in the cross channel, that's what's controlling the quality of this approximation.
So you can always show
If you know that, if you have that information, then you can get a rough idea of when these asymptotics kick in. Okay? Here you're assuming it's only the identity, but then if you have some other low-lying operator that's very close, then it will take longer to reach this regime. But yeah, you're right. As it stands, this is just an asymptotic statement. But in practice, it works very well, even for small values of E star. Okay, so conformal blocks. I don't know exactly how much Chris did. So let me just sketch the rough idea. I'll go fast because you've probably seen this already. But so the idea is that the conformal block is if you have the 4-point function for operators, then the conformal block in the S channel, where you use the OP in 1, 2, and 3, 4, can be obtained by inserting a complete set of states. Okay? Okay? So this is essentially what I wrote down before. It's the sum where you only care about the energy, so the scaling dimensions. You don't care if they're primaries. But so you can reorganize this sum in terms of a sum over primaries and their descendants. And in that case, it's useful to define something which are called the conformal partial waves. Which we can write, so sum over n, 0, and then O1, O2, then you have Pn. This is A. So I'm going to be a bit schematic here, but then we're going to do something properly. 3, 4, 0. So we're going to split the 4-point function as an infinite sum of these conformal partial waves, one for each primary being exchanged. So P stands for primary. Okay? I guess this is kind of historical terminology, but anyways, people used to work with these things, and the point is that you can write this 4-point function in the same way that you write you can write the conformal partial wave in the same way that you write the 4-point function. So there will be some prefactor depending on the coordinates xi, and then it's going to be 1, 2p, 3, 4p, 3, 4p, g delta p, lp, 1, 2, 3, 4, uv. Okay? So this is kind of like a precursor to the conformal block. Sometimes it's useful to consider. So this thing, well, it's the kinematical prefactor that carries the conformal dimension of O1, O2, O3, O4. So for instance, if delta 1 is equal to delta 2, delta 4, then this could be, for instance, 1 over x12 to delta phi, 1 over x34 to delta phi. Okay, like we did for the 4-point function at the beginning. In general, if the 4 dimensions are different, there are many choices that you can make. So accordingly, the definition of the blocks will also change, but it also changes just by some factors of u and v. So there are different conventions, but in any case, we'll mostly stick. I think we'll just do the case where all operators are identical, and we'll use this factor. Okay. But so what I want you to get out of this is that the block in general, as I said, so you go from this set from this sum where you're summing over all energy eigenstates to a sum where you're summing over the energy eigenstates which correspond to descendants of some primary state. So this is a primary state. This is a general descendant at level n. So there are n p's here, momentum generators. So these p's, they carry some indices. Okay. Same thing here for k. So the indices are labeled b. Okay, in general, there will be n indices. And then this G minus 1 is basically, it's the inverse norm of this state. Okay, so this is the state, but it's not properly normalized. So you need to normalize it, and so that's accounted for by this matrix. Okay, so you need to compute the matrix of norms of all these states, and then you invert it and you put it here. Okay, so that's the idea, which works in any dimension for any set of operators. This is the definition. Okay, but obviously this is a complicated sum to do in general, so we'll need more efficient methods to do it. But still, I'm going to show how this works in one dimension. In one dimension, you can really work out what all these things mean very explicitly. So I think it's instructive. And this will allow you to compute the conformal blocks in one dimension. Okay? So first, let us set out our conventions. So now we're going to be in D equals 1. So the generators of the conformal group are D, P, and K, with dP is P, dK is minus K, and K with P is 2D. Okay, so this is SL2R, right? It's the algebra of SL2R. The conformal group in one dimension is just SL2R, which is SO1, 2. Okay? So this is the algebra in this case, and the action of the generators on operators in my conventions are x dx plus delta of O, P with O is dx Ox, and K with O. Again, this should just be a review, because Chris, he must have written these things down already, but this is just to establish conventions. Plus 2x delta Ox. Okay? So these are my conventions. Okay, so now let's use this definition to compute the conformal block. So, because of conformal invariance, things will only depend on the cross ratio. Okay, so the cross ratio that I will use is x is x1 minus x2, x3 minus x4, divided by x1 minus x3, x2 minus x4. And I'm going to pick a configuration of points where x1 is 0, x2 is x, or maybe it's minus x. Yeah, maybe I want to define it like this. X, then x3 is 1. Ah, no, this is correct. My apologies. 1, 2. And x4 is infinity. Okay? So, according to that definition, the conformal block is G delta P of x is x to the 2 delta. And delta 1 Pn P K Ox. Okay? So I've chosen that this configuration of points. So x1 is at 0, x4 is at infinity, so we get the eigenstates of energy here. delta, delta. This x to the 2 delta, it's because of this, right? It becomes x to the 2 delta. And so the block is 1 over x to the delta times w. Okay, so it appears multiplying there. These are the descendants. This time there are no indices, so this is really correct. This is p to the n and k to the n. And then I have to divide, multiply by the inverse matrix of norms. Okay? But now there's just one descendant at each level. So the matrix is just a number, so you just divide by this, which is, so it's the norm of this state, Pn delta p, right? This is the norm. Okay, so we need to compute these objects. So the first result is that delta p kn pn with delta p is 2 delta p n times n factorial. Does everyone know what this symbol means? The Pochhammer symbol? I should write it down just in case. So a n is gamma a plus n divided by gamma a. And so when n is an integer, this is just some polynomial. So it's for n equals 1, it's equal to a, then it's a plus 1, then a plus 1, a plus 2. Okay? So this is a result. And so if you want to prove this result, it's very easy. You do it for n equals 1, you do it for n equals 2, and then you guess. This is how I did it. But then I thought maybe this would not be good enough. So there's actually a very nice a trick to compute it, which shows you really the power of radial quantization in action. So let's do the following trick. Consider the two-point function of identical operators. We already know what this is. It's 1 y minus x to the 2 delta, right? And I can write this as y to the minus 2 delta sum plus infinity 1 over n factorial 2 delta n factorial yx over y squared to the n. So I wrote it in this way simply because this is also true in higher dimensions if you write y dot x divided by y squared. Of course, in one dimension, this is just x over y. Okay? So this is true. Okay, you can just check. Do it in mathematics if you want. But we also know the following. We know that we can compute this in radial quantization as y minus 2 delta delta e to the k divided by y e to the px delta, right? So this takes the in state and constructs the operator at position x by translation. And this guy does the same thing starting with the out state. It brings it to position y. Okay? So this is the same as this. But you can just expand these exponentials, right? So this is y to the minus 2 delta minus infinity 1 over n factorial squared yx over y squared to the n delta kn pn. Right? So you expand both exponentials, you get a double sum, but this object only exists if you have the same number of k's and the same number of p's, so the double sum reduces to the one on the diagonal. The n factorial square, again, it's from the two exponentials. So, okay, so you have this. So if you compare this with this, then you get that result. Okay? So radial quantization works, if you want. Anyway, so now you can treat it as an exercise. Prove that delta O1 Pn delta P is delta P n, and delta P Kn Ox delta is delta P n x to the delta P minus 2 delta plus n. Okay? So again, you can just compute a few cases by hand if you want, or you can use the same trick. Now you need the form of the three-point function. The three-point function is known, right? So you set it in these kinematics and you expand in a power series and you read off the numbers. And this is what you get. Okay? It's exactly the same thing. And so we have everything we need. So the conformal block, this x to the 2 delta will cancel with that one. And so we get a sum delta P n, delta P n, 2 delta P n, x to the delta P plus n. You get this infinite sum involving Pochhammer symbols. And if you like CFTs, you have to learn how to love these sums and learn how to love hypergeometric functions. This is a name for this sum, if you want. But then it satisfies many identities that you cannot get from that sum. Okay? So this is the conformal block of a primary. Maybe I should put a P here, sorry. P, 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 P. Okay? So I don't know, did Chris write down the expression for the blocks in d equals 2 or something? No? So in any even dimension, the conformal blocks are roughly these things times some extra powers of x and a new coordinate, which you can call x bar. So it's like this squared in some sense. Okay, so this is not as trivial computation as it looks. It turns out to be actually useful. Okay, so this is method 1 for computing conformal blocks. This is not the way you want to do it. But it does work. So Chris also told you about the Casimir method for computing the blocks, right? Well, okay, let me be very quick about it then. So the Casimir, in the two-dimensional case, it's d squared minus kp plus pk over 2. So you can check that this object commutes with d, k, and p. Okay? So this is the Casimir. It commutes with all the generators of the group. And so C2 acting on Pn delta p, it doesn't care about n. It doesn't care about p because it just commutes with it. And it turns out that it gives you delta minus 1, which is the appropriate value of the Casimir in one dimension. So more generally, you would have m squared, so the rotations here, and you would get delta minus d plus L plus D minus 2. Okay, and the logic would be similar. It commutes with all the generators. Okay, so now the idea is that in the computation that we had there, if you insert C2 here, you already know the answer. It's what I just wrote down. But at the same time, you could commute C2 so that it acts on the other two operators, and then this will give you a differential operator. So when you do that, then you get the operator corresponding to D becomes x1 d1 plus x2 d2 plus 2 delta. LP becomes x1, no, this is wrong, d1 plus d2. And LK becomes x1 squared d1 plus x2 squared d2 plus 2 x1 minus x1 plus x2 delta. Again, so this is the generators that I wrote there. Now they're applied to two insertions, so you just get the sum. And so your mission, should you choose to accept it, is to write down an L2, which is this squared minus this times this minus this times this divided by 2. Okay? So this gives you a differential operator in terms of x1 and x2, and then you just act with that L2 on W x1, x2, delta P. This doesn't care about the other x's. And we already know what it is. It's 1 divided by x12 to the 2 delta, G of the cross ratio, which is x1 minus x2, divided by x1 minus 1, right? In that configuration of points. So we need to keep x1 and x2 general, because we are taking derivatives, but x3 and x4 we can do whatever you want. Okay? So you take this operator, do it in Mathematica, for instance, or do it by hand if you're brave. Take this operator, act on this function, and you should get back the same function times the Casimir, which is delta delta minus 1. Okay, and indeed, so let me just give you the answer. L2 minus C2 is delta P minus 1. Minus C2, maybe it's plus C2 or something. No, minus C2 minus x squared dx minus 1 minus x d2x. Okay? So this differential operator annihilates that object, this one. Okay? It's related to the hypergeometric differential equation. Okay, so again, I did it in d equals 1, but in higher dimensions, the logic is exactly the same. Okay? You just have these m squares, so you have more stuff. But if you can do this in Mathematica, you can probably do the other one, okay, to get the differential equation. But incidentally, I think Chris wrote down the differential equation, right? In terms of dz bar, some big nasty thing. So again, these are kind of like the basics of conformal blocks. Let me tell you what we use to compute them numerically. So there are two methods being used that I'm aware of. One of them is the Casimir method, and the other one is the recursion relation method. So since I just spoke about this, let me tell you about the Casimir method. Do I have time, or 5 minutes? Well, okay. Maybe it's a good time for a break before I start it.
Yeah, okay. Any questions?
Yeah, questions about this?